These are notes on Hess's law, which is chapter 17.4 in your book. If you may remember, I talked about that there are 4 ways that you can find the enthalpy change, or delta H, of a reaction. And one of them is calorimetry, and that's where you're actually directly measuring it. You're mixing things in a calorimeter, which is designed to insulate heat so that you're not losing a lot of heat to the outside. And we'll do a few review problems of that. And then the second way is Hess's law, and so we're going to introduce that today. First, though, let's kind of review calorimetry, just because this is a lot of calculating. I think you'll find the other ways maybe less calculating-y. I don't know. Some of you will disagree with me. But this one, I think, is where you really have to think about how you're setting this up. So when 50 milliliters of 0.01 molar HCl at 23.5 degrees Celsius is reacted with 50 milliliters of 0.01 molar NaOH at 23.5 degrees Celsius, same temperature, the temperature increases to 26.0 degrees Celsius. And the idea is, in a calorimeter, you're not losing a bunch of energy to the outside air. That temperature change is going to be pretty valid. Calculate the enthalpy change of the reaction in kilojoules. Assume the density of each solution is 1.0 grams per milliliter and the specific heat is that of water. Because our solutions are so dilute, the specific heat is going to be somewhere around water. Most of this 50 milliliters is water, not HCl, not NaOH. So go ahead, pause the video, set this problem up, and then you can solve for it. So this should have been the reaction you got. We're looking for the delta H of the surroundings. Remember, we can only measure the surroundings. That's where we're going to see a temperature change. So that is negative Q, because negative Q is always the surroundings. Q is the system. Negative Q is the surroundings. So it's negative Cm delta T, which is negative 4.18 joules per gram degree Celsius times 100 grams. That's the 50 plus the 50. If the density is 1 gram per milliliter, 50 milliliters is 50 grams. And then my temperature final minus my temperature initial. So you can go ahead and solve this, but remember that we're solving in kilojoules. We always give our delta H's in kilojoules, but here we're going to have, this answer is going to be in joules, so we'll have to convert to kilojoules. So go ahead and solve that. And you should get negative 1.05 kilojoules. So that's how much energy is going to be released, making this an exothermic reaction. Energy is released as these reactants produce products. Let's do another problem that you've seen before. Again, these are kind of review. These are the new concept is that we're calculating this thing called delta H, but we've actually been calculating that all along. So let's kind of review the heat of phase change. So how much heat is required to melt a 6.2 gram ice cube? Some of you are going to need to go back into your notes to figure this out. That's okay. You can pause, you can look back. It is in chapter 17, so if you've got your book with you, you should be able to look that up pretty easily. So you should have gotten this equation, Q equals N times delta heat of fusion. And we're looking at the delta heat of fusion of water. So we get 0.34 moles, and then times 6.01 kilojoules per mole. That's the amount of energy it takes to melt 1 mole of ice into water, liquid water. And that ends up being 2.1 kilojoules. The 0.34 came from converting the grams, the 6.2 grams to moles. I didn't show how to do that. I assume by now you know, but if you don't, you're going to multiply it by 1 mole over, it's about 18 grams. And so this process we see is endothermic. It's requiring heat. So the end products have more heat than, or more energy than the reactants did. The liquid has more energy than the solid, and it got that heat from the outside, or from its surroundings. So if we were measuring this in a calorimeter, we would have expected the temperature to decrease. So let's do a different form. By the way, while I said, let me go back for a second because this may have confused some people. While we would have expected the temperature of the surroundings to decrease, we would have expected the temperature of the ice, remember, to stay the same, because as something goes through phase change, its temperature stays the same. It's using that energy not to heat up, but to break bonds apart. Those are the intramolecular forces. Intermolecular forces. Intermolecular forces. The forces between the molecules. We're breaking those up using that heat. So do you kind of remember that concept? That's with the lauric acid. If you remember the lauric acid lab, as the lauric acid froze, we heated it up, made it liquid, put it in water, let it freeze. The temperature of the water changed. That would be the surroundings. The temperature of the lauric acid did not. And that's how we calculated how much heat was required to be removed to freeze the lauric acid. That may be something you want to go back and look at. So then let's look at this, a little different. How many grams of ice can you melt with 15 kilojoules of heat? So it's kind of the reverse of the previous question. So go ahead, pause the video, figure it out, and then check your answer. You should have gotten 15, this would be your equation, 15 kilojoules equals N, number of moles, we don't know how many moles, times 6.01 kilojoules per mole. So then we're going to solve for N, that's going to give us moles, and then we can convert that to grams. So we should get N equals 2.5 moles. Oh, I've got my equal sign in the wrong place. That should be, let me fix that here. So this, obviously this equal sign should be right there. So it's N equals 2.5 moles, which equals 45 grams. Again, I assume at this point you're pretty conversant in converting grams to moles and moles to grams. If you're still confused by that, please make sure you get help. Ask in class, look it up in your book, do something, because I'm assuming by this time you know it. So now let's look at our new concept, Hess's law. And this is another way to get enthalpy change. There are different ways. You don't always have a nice little equation that you can set up. You can't always do everything in class to measure the heat changes. Sometimes you need to use other resources. So it's just a different way of getting at the same quantity. Hess's law is if you add two or more equations to get a final equation, you can also add their heats of reaction, delta H, to get the overall enthalpy change. Okay, so let's look at what that means. It's essentially talking about the sum of the parts equals the whole. Okay, and I'm going to show you kind of like what a picture of this looks like in a minute. But there's a couple of things. Sometimes you need to change equations around. So if you reverse the reaction, that's going to change the sign of the delta H. If you multiply the reaction by a coefficient, that's going to multiply the delta H by the same coefficient. And those two statements I realize are a little confusing right now. We're going to look at some examples. And hopefully that will help make sense of this. We'll do a couple of examples on that. So let's look at kind of a graph of what that means. So this is a more, here, let me get a pen here. This is a more general graph of what Hess's law means. That if you have reactants A and you're going to products B, and there is some sort of delta H, so this as enthalpy, this graph enthalpy is increasing, going in the upward direction. Meaning, going from reactants A to products B, you're going to lose energy. You're going to release energy. This is going to be an exothermic reaction. If that reaction is actually a combination of two reactions, sometimes you have what are called intermediates, which are that there might be some intermediate products that the reactants don't react completely. They go to an intermediate reaction and then to the products. It's not just A to B. It's almost A to A1/2 to B. Nope, there's the bell. We'll wait for that. That as the reactants go to their intermediate, say A1/2, perhaps that's going to take energy, but then from the intermediates to the products, that's going to release energy, and that the sum of these two, this plus this, ends up being the delta H. And that regardless of what path you take to get from A to B, you're always going to have the same delta H if you add up all these arrows. So here is a quantitative look at that as we go from carbon plus oxygen gas to carbon dioxide. That path releases 393.5 kilojoules of energy. Okay, so that's, again, exothermic. This is also true of endothermic reactions. I just happen to choose an exothermic one. So, in fact, in this case, there is an intermediate product where the carbon reacts with half a mole of the oxygen gas, and you get carbon monoxide. And that process releases 110.5 kilojoules of energy. Then you get the carbon monoxide reacting with half a mole of oxygen gas to give you the carbon dioxide, and that releases another 283 kilojoules of energy. So if you add these two together, you end up with the total. So let's look at how that works if you have equations and you already know their delta H's and you want to combine them into a final equation. So let's look at the enthalpy change of diamond to graphite. We normally think about diamonds as coming from graphite or coal or some kind of carbon. That most of us know that diamond is just carbon and graphite is just carbon, but that the carbon atoms are arranged differently. They're much more orderly in diamond than they are in graphite. They're kind of all over the place in graphite, just a lump of carbon. And we think about that as going graphite to diamond. We know that, with a lot of heat and pressure, graphite can turn into diamond. But in fact, diamond also must be able to turn back into graphite. And I'll tell you something interesting about that after this problem. So what we're really looking at is carbon in solid form as diamond going to carbon in solid form as graphite. And it's possible that we can't find a delta H for this, but that we have delta H's for other reactions. So here are two reactions that are known reactions. And one of the things to know is delta H is always determined experimentally. So occasionally you're going to see slightly different values for delta H because it's always determined experimentally. There is no way to calculate a delta H that's not through experiment. So that's something to kind of keep in mind. You'll see different delta H tables, especially when we start talking about heats of formation, that are different depending on which table you look at, because they're also averages because they're experimental. So it depends how many things you've averaged to get your final quantity. So, and we'll talk about why we don't just have a delta H for diamond to graphite, because I know some of you are saying, well, why don't you just look up one? So we have carbon solid as graphite plus oxygen gas giving us carbon dioxide. That is, in a sense, what we just looked at with the graphs. And that gives us a delta H of negative 393.5 kilojoules. We can also, though, look at carbon as solid diamond plus oxygen gas, giving us CO2, and that's got a slightly different delta H because the atoms are different in diamond than graphite, and so it's going to take more or less energy to change them around depending on which one we're talking about. So notice, though, and this is going to go back to what I was talking about with the reversing reactions and things like that. In our overall reaction, we want diamond in the reactants, which is what we have in this reaction, but we want graphite in the products, which is the reverse of this reaction. Okay, there's the bell again. So here we've got diamond in the reactants, which is exactly what we want, but we're going to need to reverse this reaction to get graphite in the products. So we can take reaction A and simply reverse it. Carbon dioxide becomes our reactant, and then graphite and oxygen gas are our products. But now what we've done with the delta H here is we've reversed the sign. That essentially, if it releases 393.5 kilojoules of energy to go in this direction, then it must take 393.5 kilojoules of energy to go in this direction. And then for reaction B, it's exactly what we wanted. We wanted the diamond in the reactants, and it is. So that's just the exact same reaction. We haven't had to do anything with the delta H. And now we can essentially eliminate anything that is in both the reactants and products. Essentially, things in the reactants of one equation and the products of another will cancel out. So here we have carbon dioxide gas as a reactant, so we can cancel that with the carbon dioxide gas here as a product. Here we have oxygen gas as a reactant and oxygen gas as a product. And so what we're left with is the diamond in the reactants, which is what we wanted, and the graphite in the products, which is what we wanted. So that's our overall reaction. And so then we add these together, 393.5 plus negative 395.4 gives us negative 1.9 kilojoules. And so as diamond turns to graphite, it actually is going to release a small amount of energy. Now, one of the things we're not going to talk about this year, but you'll talk about if you do AP or if you go on to college chemistry, is something called entropy. So it's almost the sistership of enthalpy. You talk about these two in conjunction a lot. But once you start understanding enthalpy and entropy, you can start talking about what types of reactions happen spontaneously, just by themselves, without any help from us. We notice, for example, in our world, there's an awful lot of liquid water, but not as much hydrogen and oxygen gas. So something about hydrogen and oxygen gas reacting must happen spontaneously. If we want to get the hydrogen and oxygen gas from the water, we must we can do that, but we must have to do something in order for that to happen. Similarly, interestingly, diamond converting to graphite is a spontaneous reaction. That just happens. Over time, diamond will turn to graphite, not the other way around, which is kind of crazy since we invest all this money in, diamond jewelry. But the other thing we won't talk about this year, but again, you'll get in AP or if you go on to college chemistry, is reaction rates. Not all reactions happen in the same amount of time. Some happen very quickly. Some take a lot more time to happen. And some are so slow that it happens over, I don't even know, millions or tens of thousands of years. This reaction of diamond to graphite is actually spontaneous, but it happens so slowly that we will never ever see it happen in our lifetime. That it's perfectly safe to invest in your diamond jewelry because you're not going to see it turn to graphite anytime soon, even though that is a slow change that is happening in every diamond out there. All right, interesting facts about diamonds and graphites. Diamond and graphite being pencil lead, by the way. So now let me give you one that you're going to do on your own. So we're looking at 2 carbon solid plus gaseous water. Okay, so that's something we haven't really talked a lot about, but here we would need to make gaseous water for this to happen. Yields methane gas plus carbon dioxide gas. So there's no way you can start this without having some given known equations. So I'm going to give you these 3 equations, and I'm going to tell you you need to use all 3. And I give you their enthalpy changes. And so now I want you to pause the video and see if you can figure out what the enthalpy change, the delta H, is for this above reaction, the carbon plus steam, yielding methane and carbon dioxide gas. But, and by the way, this is a process used to turn coke or coal into usable gas. So this is one of the ways we get energy out of our coal. And then the other thing I'm going to say is, I at least struggle to do this in my head. I always want to do it in my head. I think I should be able to do it in my head, and I really can't. I always get out a piece of paper and a pencil, and I have to kind of scribble around and change things around. So some of you may be able to do this in your head. That's great. I struggle to keep everything kind of straight in my head. So see what you can get to. Pause it, and then you can check your work. Go ahead. Okay, so what I'm going to do is I'm going to take this equation, because I know, and this is actually equation C, so I'll put a little C here so that you can follow what I'm doing. And I'm taking C because C is the only thing with methane gas in it, and I know that I need methane gas in my products. So I'm going to reverse C. I'm going to take the reactants and make them products, and take the products and make them reactants. I'm simply reversing the reaction, which is then going to reverse the delta H. So I'm also going to put a little check there. I've got my methane. So then my next thing I'm going to look at is my CO2, because again, I only have one thing that's got CO2, and I need CO2 in the products. So here is my reaction B. And notice in reaction B, carbon dioxide is in the products. I need it in the products, so I don't have to actually do anything with that reaction. I'm just going to write it down. So check that one off too. So now the only reaction I have left is reaction A. And reaction A, I've got carbon in the reactants, just like I need carbon here. But notice in my reaction, I need 2 carbons. So what I'm going to do is I'm going to multiply this entire reaction by 2. Okay? And that, as I said before, is going to multiply my delta H by 2. So here is that reaction. This is reaction A. It doesn't matter in which order they put them. I put them. You can put them in whatever order you want. I've multiplied the entire reaction by 2, so there's a coefficient on each reactant and product. And then my delta H is also multiplied by 2. And so now I definitely want to check my work here. So I notice here in the reactants I've got an H2O, and here I've got an H2O, so those are going to cancel out. And then here I've got 2 carbon monoxide, COs. Here I've got 1 carbon monoxide and 2 carbon monoxide, so the coefficients matter here. I can't just take out things where the coefficients don't cancel. Notice I kept in my 2 H2O here because there's not 2 more H2Os to cancel that. But here I can cancel out my 2 carbon monoxides, carbon monoxide and carbon monoxide. Had I only had 1 carbon monoxide over here, I could still cancel out one of these, but it would have left one as well. Then I can cancel out my hydrogen gases. Here I've got 3 hydrogen gases, and here I've got 1 hydrogen gas and 2 hydrogen gases. And what I'm left with is my 2 carbons, which is what I wanted. Check. Wait a minute, somehow I have picked up an extra H2O. Where did that H2O pick up from? Oh dear. All right, let me pause this and figure that out. Okay, so I figured out the problem. That's the good news. This actually isn't properly balanced. This should be a 2. Because you'll notice here I have 4 hydrogens. Here I only had 2 hydrogens. So I had left out the coefficient there and that wasn't balanced. So I'm good. I've got my 2 carbons, my 2 H2Os. That was probably my mistake when I just typed in the equation. My 1 methane. There's my 1 methane, my 1 CO2. And then I add these up, negative 206.1 plus negative 41.2 plus positive 262.6. And my overall reaction, like I did it again, here's my 2, is a delta H of 15.2, positive 15.2 kilojoules. So this reaction is going to consume energy, which is interesting because if you remember, I said this is one of the ways we convert raw carbon, coal, or coke into methane gas. But notice it's taking energy in order to get us, I'm going to kind of put this in quotes, get us energy. Obviously, any energy you use, you're simply converting from energy somewhere else. But if we did some reactions on burning methane gas, you would see that the delta H we get from burning methane gas in the presence of oxygen is so much larger than the delta H it took to make the methane gas. So we're getting out a lot more energy than we're putting in to make that, which is why it makes it such a useful energy source. All right, please feel free to ask questions online or in class. This is a very new concept. We're manipulating a lot of stuff here. Good luck.